251.9 million years ago, Earth experienced the most severe extinction in its history. The Permian-Triassic boundary marks the greatest die-off of life ever recorded, wiping out 81% of marine species and 70% of terrestrial vertebrates. Known as the Great Dying, this event ended the Paleozoic era and began the Mesozoic. It was the deadliest of the 5 major mass extinctions in the Phanerozoic eon. The extinction eliminated 57% of biological families, 62% of genera, and devastated entire ecosystems. Insects, too, suffered their greatest known mass extinction. Scientists now date this event with millennial precision. Using uranium-lead zircon dating from volcanic ash beds at Maishan, China, the extinction window was pinned between 251.941 and 251.880 million years ago. The boundary is defined by the first appearance of the conodont fossil Hyndeiditis parvus, a microscopic tooth-like structure used as a global marker. The leading cause of the Great Dying was the eruption of the Siberian traps, a vast flood-basalt province in present-day Russia. These eruptions span hundreds of thousands of years, releasing massive amounts of carbon dioxide and sulfur dioxide into the atmosphere. Atmospheric carbon dioxide levels surged from 400 parts per million to as high as 2,500 parts per million. Between 3,900 and 12,000 gigatons of carbon entered the ocean atmosphere system. The eruptions ignited coal and oil deposits, releasing additional greenhouse gases and toxic compounds into the environment. Methane clathrates destabilized, releasing potent methane into the oceans and atmosphere, accelerating global warming. Novel methanogenic microbes may have thrived on minerals dispersed by the eruptions, producing even more methane. Some researchers propose an extraterrestrial impact. The Araguaia crater in Brazil as a contributing factor, triggering seismic methane release and ozone destruction. Increased ultraviolet radiation reached Earth's surface, causing mutations in plant spores, evidence of a damaged ozone layer. Marine life faced catastrophic changes. A sharp drop in 14C, a negative carbon isotope excursion of 4 to 7% signals. Massive disruption of the carbon cycle. This isotopic shift, lasting about 500,000 years, coincides with the extinction and helps identify the boundary in undatable rock layers. Oceans became acidified, and warm global temperatures rose by 8 degrees Celsius, 14 degrees Fahrenheit, making survival difficult for shell-forming organisms. Euxinia oxygen-starved sulfurous oceans spread globally. Hydrogen sulfide poisoning killed marine life and altered ocean chemistry. Bioturbators, organisms that mix sediments, nearly vanished. Their absence erased the mixed sediment layer in many marine deposits. Calcium carbonate skeleton builders were hardest hit. Organisms dependent on stable carbon dioxide levels could not adapt to acidification. Endemic species, those restricted to small regions, fared worse than cosmopolitan ones. Localized bivalves faced higher extinction risks. Marine invertebrates lost 2086 out of 329 genera in South China sections. Brachiopods, corals, and fusellinids collapsed. Only a few groups survived: articulate brachiopods with hinges, ceratid, ammonites, and crinoids, sea lilies that nearly vanished. On land, 70% of vertebrate species disappeared. Forests collapsed, and soil erosion increased dramatically. The fungal spike hypothesis suggests a surge in Reduviasporanites, once thought to be fungal spores feeding on dead organic matter. But Reduviasporanites may actually be algal remains. The fungal spike wasn't global and didn't always align with the extinction boundary. New chemical evidence supports a fungal origin, weakening earlier criticisms and reviving the decay zone hypothesis. Plants took longer to decline than animals. Pollen and spore records show vegetation collapse lagged by hundreds of thousands of years. In East Greenland, terrestrial and marine extinctions began together, within 10,000 to 60,000 years of each other. But in the Karoo Basin of South Africa, the Dicynodon to Lystrosaurus zone shift suggests land extinction preceded the marine event. In South China's Senjagu Formation, terrestrial ecosystem collapse occurred before the marine crisis. Conversely, in tropical regions, some studies suggest land extinction followed marine collapse. Was the Great Dying a single event or multiple pulses? Evidence from Meishan suggests one main peak, but Liangfengye section data reveal 2 distinct waves, MEH1 and MEH2, each with different causes. At Shenxi, 2 pulses appear again, separated by ecological recovery attempts. Ostracods and brachiopods went extinct 670,000 to 1.17 million years apart, suggesting staggered losses. Marine environmental stress in the Bowen Basin, Queensland, began in the middle Lopingian, long before the final extinction. Species richness declined earlier than ecosystem collapse by about 61,000 years, indicating a decoupling of biodiversity and structural integrity. The Capetanian extinction, 7 to 10 million years earlier, complicates the picture. Many losses once attributed to the Permian-Triassic event may belong to this prior crisis. Dinocephalians and Verbicinidae foraminifera died out at the end, Guadalupean, part of the Capetanian extinction. Some scientists argue for a prolonged extinction event. Two major pulses, 9.4 million years apart, with elevated extinction rates between them. Under this view, the final pulse killed 80% of marine species alive at the time, while earlier losses occurred during the Capetanian or interim period. The Great Dying reshaped life on Earth. The early Triassic was a time of low biodiversity and slow recovery. Lystosaurus, a hardy herbivore, dominated terrestrial ecosystems in the aftermath, becoming one of the few success stories. Marine ecosystems took millions of years to recover. Ammonites and crinoids slowly diversified in the Triassic seas. The event underscores Earth's fragility, a reminder that climate, chemistry, and life are deeply interconnected across deep time. Today, carbon dioxide levels are rising again, now at 426 parts per million. The Great Dying serves as a deep time warning of what unchecked carbon emissions can unleash. The fossil record at Maishan, China, stands as a monument to Earth's most profound crisis, a chapter written in ash, isotopes, and silence. In the deep past, we find echoes of our future. The Great Dying reminds us, extinction is not just an end, but a threshold.